13F is all about parametric equations. So when we have a point or a particle that's moving in space, we want to know the shape of its path, and we know how to do that. That's just its locus, generally in 2 dimensions. We also need to know, for instance, how fast or how slowly this particle is moving and where is it at a specific time. So for instance, imagine a ball being kicked. You want to know how fast it's going and when it will reach the goalpost. So if we're looking at where and when a particle is at a particular point along its path, we need to introduce a new variable for time t. So what we do is, instead of having a function just in terms of x and y, a Cartesian equation, we want to write our x-coordinate as a function of time and our y-coordinate as a function of time. This is called parameterization. So we see how x changes over time and how y changes over time. So for instance, by parameterizing an equation, we can see not only the shape in 2 dimensions, but also how the particle is moving. Example 1. Let's use this example to clarify. Imagine you're in a cliff diving competition at the Red Bull World Championships. You need to know exactly where you'll be in space when you jump in order to execute your dive perfectly. So we can say your horizontal position is given by x equals t, and your vertical position is given by y equals 3t squared minus t cubed. These are parametric equations where t just represents time in seconds. First part, find your position or the diver's position after 0, 1, 2, 3, and 4 seconds. So what we do is we create a little table with time in one column, or t. We have x in the next column, and we know that our equation for x is x equals t. And in the last column, we have y equals 3t squared minus t cubed. What we simply do is substitute the values of t in for 0, 1, 2, 3, and 4 for the x and y coordinate to figure out where the person is at that particular point in time. So when time is 0 seconds, the x coordinate of that person, well, x would just be t is 0, x is 0. Y coordinate would be 3 times 0 squared minus 0 cubed. Everywhere you see a t, you're just putting a 0. That means after 0 seconds, the person is at 0, 0, the origin. After 1 second, everywhere you see a t, you're going to put a 1. X will be 1, y will be 3 times 1 squared minus 1 cubed. That's just going to give me 2. So after 1 second, the person is at coordinate points 1, 2. When x is 2, or there are 2 seconds gone past, y will be 3 times 2 squared minus 2 cubed. Y will equal 4. So the person is now, say, 2 meters to the right and 4 meters in space taking their dive. After 3 seconds, the x coordinate of the person is 3. The y coordinate of the person, again, sub 3 into your y equation wherever you see a t, and you'll get 0. So they're on the way down from the dive. They're now hitting the surface of the water. And lastly, when t equals 4, we sub it into our 2 equations. We'll get x equals 4 because x is just t, and y will be equal to negative 16. So the person has now dived so deep, they are minus 16 meters or 16 meters below sea level. Let's sketch it on a graph. For 0 seconds, the person is at the origin. For 1 second, the person is probably 1 meter across, 2 meters up, so they're trying to climb up to their cliff. I'll draw this one in black because it's a bit hard to see in yellow. After 2 seconds, the person is now 2 meters to the right and 4 meters up. So they're probably at the top of the cliff that they're going to jump from. Between 2 and 3 seconds, the person has jumped off their cliff and they are breaking through the water. Hopefully their dive went well. And after 4 seconds, we're right down the bottom. My graph will not really be to scale at 4 minus 16. If I join all these points together, I probably get a rough indication of what the graph of the person is. This is the graph of their dive. We're going to now convert from parametric form into Cartesian form. So parametric is when I have x equals something with t and y equals something with t. To convert into Cartesian form, what we have to do is remove the t's. I want y equals something with x in it only, and maybe some constants. To eliminate the t's, we just use substitution. So for instance, in this equation, I know that x equals t. That's my equation 1. My equation 2 is my y equation. Let's sub x equals t from 1 into my equation 2. So everywhere you see a t, you are just going to put an x. Let's see what happens. We'll get y equals 3. I'll now have x squared minus x cubed. This is my Cartesian equation of the parametric equations given in the question. Now, hopefully my graph of that time, that upside down parabola, should match the graph of y equals 3x squared minus x cubed. Left, you can see the Cartesian equation. That looks pretty similar to the graph we drew. On the right, we can also see our parametric equation. And now I can see the particle traveling over time. And we do see, besides the scale, these both represent the same curve. Brilliant. Let's try this with example 2. Okay, a particle is moving with respect to time. X equals 3t and y equals t squared minus t for time between 0 and 3 seconds. Question A, find its position at 0, 1, 2, and 3 seconds. So again, we do the same thing. I always draw a table. So I have time in the first column. I have my x coordinate, or my x equation, and then my y coordinate or y equation for the given time. You know what to do here. If t equals 0 seconds, so x, when we have t 0, would have x equals 3 times 0, that's 0. Y would be, well, 0 squared minus 0, y is 0. For the next one, 1 second, let's sub it in. We'll have x equals 3 times 1, just 3. Y equals 1 squared minus 1, that's 0. That's nice. 2 seconds, we'll have 3 times 2 now. X will equal 6. Y will equal 2 squared minus 2, that's 2. After 3 seconds, my x coordinate will be 9, 3 times 3. And my y coordinate will be 3 squared minus 3, that will be 6. Okay, now I know the coordinate points of where my particle is at these given specific times. So instead of sketching first, we're going to convert the equation from parametric into Cartesian form. So rewrite out our two equations, and remember we have to eliminate the t. So again, we use substitution, but the first thing you want to do is take your x equals 3t and make t on one side by itself and the x over 3 on the other side. So by rearranging, I just divide both sides by 3 and I'll get t equals x over 3. So I'm going to use that equation and sub it into my y equals t squared minus t. When I do that, everywhere I see a t, I'm going to put x over 3. So I get y equals x on 3 squared minus x on 3. I'm going to write it as y equals x squared over 9 minus x on 3. So my graph should look like a parabola when I draw it. Let's have a look. Okay, now you could try and join these together, but you're missing information if you don't look at your Cartesian equation. So the Cartesian equation is actually a parabola. So your graph will look like this. It's actually curved. The parabola opens upwards, and in further detail we can have a look and confirm that we drew it right. Of course, you can use your Cartesian equation just to double check that your drawing is correct. Over time, let's see. 1 second, 2 seconds, now, and then 3 seconds. That looks like exactly what we got.